So I was saying that this one is so regarding linearity and space invariance. So the linearity part, I hope is fairly clear, right? So okay, so the linearity, right? We saw last time itself that I mean you have this lens and you have the image plane here. And we said that we could have not just one point light source, we could have multiple point light source, and all of these of course will typically map into some kind of a blur circle, right? And wherever, let us say, they all probably converge, right? For this point they converge here, create a blur circle, then the other one will have its own blur circle, and then we showed that if there are multiple number of them, they will all add up together, right? So on the image plane, it's just that right, all these blur circles will come together. Just a superposition holds, and then you know what intensity you will get there. The second notion is more tricky. The second notion is about space invariance, spatial invariance or space invariance, right, as it is called. This one requires some amount of thought. Now, by spatial invariance, right, if it is a 1D case, okay, we say that if x of t is given to a system and if it produces y of t, okay, whether it is linear or not, we don't care. But if I shift t by t naught, then for any arbitrary t naught, y should also shift by t naught, right? T naught can be positive, negative, whatever, it doesn't matter. Okay, and this could be a system that is linear or not, we don't care. The shift invariance does not have anything to do with linearity. They are all independent notions, right? So similarly, okay, what we want to ask is, if I had an image, right, I mean that that if I were to shift it by some amount, delta x, delta y, and in here, right, you should note that this is all a global shift, right? This is a global shift, no? Every x, I mean, so that t naught is applied everywhere, correct? We don't keep changing t naught. So the entire signal is shifted to the right or to the left exactly by t naught. So similarly, okay, we want to look at an image. Assume that right, I of xy goes in. Okay, if I take a continuous case, okay, assume that I of xy goes in and it produces g of xy. And our interpretation, I think last time itself I told you that I of xy, the interpretation is that this is a pinhole focused image that you would have seen had this lens not been there. And in the place where the aperture is, if you replace it with a lens, then whatever is the image that you see, that becomes your g, correct? That's the output of this imaging system. Then if you do I of let's say whatever x minus x naught or delta x, let's say, and then y minus delta y, all on the image plane again. Delta x, delta y is on the image plane. So it's like if you can globally shift the image to right, left, top, bottom, then g, right, we want to check whether g also shifts by x minus delta x, y minus delta y, right? If this doesn't happen, then we know that then we can declare that this is not shift invariant or this is not spatially invariant. And we would like to have a system that is actually spatially invariant, right? Yeah.
So is this mean that the center of the blurred image will be the pinhole point?
The center of the, say that again, does it mean that?
A point from a view from pinhole will result in a point on image.
Correct.
Does this mean that the center of the blurred part
Correct.
Is a pinhole point?
Exactly. So it basically means that if this lens itself were to bring that scene into focus, then I and G will be exactly the same. G will be equal to I, at every point to point they will match, and that intensity, because there is no longer a blur circle, there is only a point. So whatever you saw with respect to pinhole, the same intensity you will now see at the central ray. There is no circle around it, correct? Okay, now the point is, right, so delta x, delta y, so what does it mean to translate an image now? Correct, I mean, we have to understand, no, because in 1D it's very easy, we just write x of t minus t naught and ask for y of, whether the output is y of t minus t naught. Now, as far as an imaging system is concerned, we have to first of all ask what does it mean to shift this input image now, the I of xy, what does it mean to shift it globally? Okay, and then we can see whether the output is shifted. So here is where sometimes, right, people tend to interpret things in a sort of a different way and end up concluding that the lens is shift variant. Okay, actually it is not. If you can provide to the lens an image that is globally shifted, the lens will give out an output that is also globally shifted. The fact that you cannot produce that input, right, cannot be used to blame the lens. Okay, I'll tell you what I actually mean by that. Okay, now imagine that let's say Let's now if you go back, okay, now what are the key things, right, that we want to again borrow? I told you we do a pinhole because there are many things that we borrow from there, okay, in order to be able to understand right, what is happening here. So one of the things that we saw was the central ray, right, in a lens, okay, the central ray, okay, as this boy was telling just now. So the central ray, right, we know that this ray obeys this ray, the central ray. Okay, last time I think I wrote the central ray obeys the perspective projection model, the perspective projection equation model, right? Whatever, right, you want to call it. Which means that, right, out here you can apply your similarity of triangles, and then you can show that the shift, right, if you compute. I mean, all that we did, right, with respect to the focal length, all that, right, the image coordinate, how it will be related to the world coordinate, all of that is obeyed by the central ray. And what is also important to realize is that the image is getting formed, right, I mean, by the center, through many blur circles getting formed around the central ray, correct. So the central ray is is a kind of unique ray in that sense. It has all these relations that it borrows from actually a pinhole model. And then the blur circle is in fact formed around it. So the point is, when you say that you want to shift I of xy to, so I of xy is really a pinhole equivalent now, and we are trying to say that I want to get I of x minus delta x, y minus delta y. And imagine that you have a point, let's say P, okay, in the scene. Let me go back to black. So if I have a point, let's say, right, there is some point P here, okay, and let's say, right, the other point is some Q, okay. Now if P has, let's say, coordinate x1, y1, z1, and Q has coordinates x2, y2, z2, okay. Now shifting the, I mean, you can either talk about shifting the scene, or you can talk about shifting the camera, okay, both are the same, right, it's simply a relative motion. Now if you think about, just to make matters easy, right, imagine that this camera, right, I actually move by an amount delta x delta y, okay, I am kind of moving the camera by, I mean, so this is in the world coordinate, I am kind of moving the camera by an amount to say delta x delta y, or you can equivalently think of the scene moving by an amount delta x delta y. Now what will happen is, this coordinate, right, we know that the image coordinate for P will be some small x1, right. Before you move, it will be x1 is equal to fx1 by z1, y1 will be fy1 by z1, and after you move by an amount delta x delta y, so you will have a new one which is x1 dash, which will be f of x1 plus delta x, okay, by, okay, now the point is, right, if okay, so since your z1 hasn't changed, it is still z1, so you get fx1 by z1 plus f delta x by what is that, delta x by z1. Similarly, you can show that, y1 prime will be fy1 by z1 plus f delta y by z1, correct. Now if you look at the shift, okay, so it's like, if you look at x1 minus x1 prime, okay, the amount of shift that is given by f delta x by z1, and a y1 minus y1 prime is f delta y by z1, okay. For Q, you can say similarly show that if for Q you are using 2, right, so if you say x2 minus x2 prime will be f, the point is, right, this guy will go like, fx2 by z2, fy2 by z2, then x2 plus delta x, y2 plus delta y. If you just carry out this operation, you will end up with f delta x by z2, and y1 minus y1 prime will be equal to f delta y by z2. Okay, so then what it actually means is that, I mean, we cannot take an arbitrary 3D scene, okay, and sort of assume that now if I capture the next image, which will be a pinhole image, let's say, that is my next eye, right, the one that is sitting here. It is not true that all of them have moved by the same amount of delta, what is this, the small delta x. So this is your small delta x, this is your small delta y, but then here it is like delta x2, delta y2, here it is delta x1, delta y1, because they both are not at the same depth, right, with respect to the camera. So which again brings us back to this fronto-parallel kind of a plane notion. So, only if you have a frontoparallel plane in front of a camera, frontoparallel in the sense that this plane is parallel to the sensor plane, then whether you move the camera or whether you move the plane by delta x, delta y, that is the only time when all the points move by an amount which is exactly the same. That means all of them will move by an amount which is given by f delta x by z, because then all of them are at the same depth z from the lens. Right? In no other situation will you be able to create an image that you can write as I of x plus delta, whatever, x minus delta x and y minus delta y, because there is no constant delta x, delta y that is applicable all over the image. Okay, so first of all, when even to get a think about when this will happen, we have to be careful. It doesn't mean that we can do it anytime, right? No, whenever we wish, no. It can only be done under certain conditions only, this will happen. Okay, but that is not, but then the point is, right, what we have to understand is, to say that x of t minus t naught exists, similarly we have to think about when will I of x minus x naught exist, and when it exists, is my output g of x minus x naught. Correct. So, we have to give a globally shifted input. Now, all that we are talking about here is when can we even do that. So, we can do that in a kind of a frontoparallel situation. So, but that is the case when we can actually talk about, at least even going from here to here, forget about what the lens is doing, right. I am not even brought in the lens yet. I am just saying that if I wanted to create a pinhole shifted equivalent, only at a certain situation I will get x minus x naught, y minus y naught, not always. Correct. So, even to do this, I assume a frontoparallel scene, right. On a frontoparallel scene, this you can do. You can move by a capital delta x, a capital delta y, and I leave it to you to think about what will happen if I move the plane along z. I said this way, right, delta x, delta y. What if I moved it along like this, along z, right? You think about it, what will happen. So, this is the only situation when you have a frontoparallel scene and the camera moves like that, right, in its own plane by an amount capital X, capital delta, or the plane moves like capital delta x, delta y. Then all the points move by an amount which is small delta x, small delta y given by f delta x by z, and so really, right. So, for that situation, this will turn out to be everyone will move by f delta x by z and f delta y by z. Delta x, delta y is the actual motion, right, in the kind of world coordinate, and on the image plane it will translate to f delta x by z and f delta y by z, irrespective of wherever you are on the plane. All of them will get shifted by that amount. Now, we want to examine what will happen to g now, right. So, if you actually think about it, so originally, okay, what we had was, let me show it with some green color. So, if you had this Q point, okay, it went here, so we had the central ray that was actually hitting here, and then we had a kind of a blood circle there. Now when this when you're doing this delta x, delta y, whatever, capital delta x, capital delta y shift, okay, imagine that, right, because of this blood circle shifts somewhere down. If you were to think of the pinhole equivalent, right, so what will happen because of this point, instead of appearing here, it would have appeared somewhere else, that shift being equal to f delta x by z. Now, what will happen the moment you introduce a lens, you will, if things are not in focus, this is a frontoparallel plane, if you wish you can bring it into focus, well, let us say it is not in focus, then what will happen, you will get actually a blood circle around the central ray again, correct, okay, because I mean, right, all that has happened is your blood circle has shifted from wherever it was, it has gone to another place, but not arbitrarily. It has shifted exactly by the same amount, because the central ray has got shifted by that amount, f delta x by z, f delta y by z, because that is the one that will follow still a pinhole law, which is a perspective, this one, a projection law, and then all that happens is the blur, and then you also know that the radius is not going to change because your z hasn't changed. So, it is identically the same blur circle coming and relocating itself, right, somewhere nearby, depending upon how much you move. So, in that sense, g of xy, right, has now moved on to g of x minus x naught, okay, and then what is not x minus x minus delta x, y minus delta y, okay. This is okay. I mean, do you have, because this is something I want you to understand, because you know what, later when you read anything more advanced, right, you should be able to map back to simple situations. Okay, that is the reason why I feel it is important to at least know. This is fairly clear as to what we mean by this invariance notion now, because what happens is, right, people sometimes write that a lens is shift variant, because what they are looking at is If I give a general 3D scene, then I'll get a space variant blur, and therefore where is this notion of space invariance and so on. What we have to remember is, just as in 1D, what do we say? X of t minus t naught. That means what you are able to generate x of t minus t naught. When you can generate x of t minus t naught, am I getting y of t minus t naught is what we are asking. Similarly here, we should look at first of all the situation that will give us an I of x minus x naught, y minus y naught without even having that. Where is if you can't even give a globally shifted input, what is the point in even asking whether my output is globally shifted? Right? So first of all, the input should come shifted globally. Which, of course, because it's a lens, it poses certain conditions on when you can do that. But if you offer a globally shifted input to this lens, it will give you a globally shifted output. That is all we care as far as space, as far as shift invariance is concerned. Give me, right, show it a globally shifted input. I don't care how you are going to show it. If you can show that, it will give you an output that is also shifted. Right? Yes. Exactly. So in that case, it won't be a global shift. That is the whole point. So even getting this suppose you call the next one as I dash, they're only under certain conditions when you can actually get this one global shift. What will happen if you shift it along, you just shift the image plane? What do you think will happen? Let's say it's a fronto-parallel plane. Actually, that holds even if you have a 3D scene, by the way, that law. Actually, it can be mapped as a homography. I will leave it to you. It's actually a homography. Those two images, you'll get another image, right? Think of it. Don't even look at the lens. Look at a pinhole case. I have an I, and now I kind of move the image plane along Z. I'll get some I dash. The first question that you might want to ask is, can I relate I and I dash through some means, through a homography? The answer is yes, and it's irrespective of whether the scene is 3D or not. You don't need a fronto-parallel plane, by the way. Okay, but I'm saying, but that is not the I dash we want. That won't give you delta x delta y. Okay, this is okay. Then, okay, so therefore, right? So therefore, overall, okay, if you all agree upon this, that if you give a shifted input, then it will of course give a shifted output. The output exactly being shifted by the same delta x delta y, no alpha times delta x and alpha times delta y and all. Okay, on the image plane, it moves exactly by the same amount, which then means that, and therefore, right, a lens is actually LSI, right? That means it's linear as well as shift invariant. Now let me now what you have to kind of realize is that if you had a 3D scene, then of course it will introduce a blur that will be spatially varying. That does not render lens as shift invariant. Simply means that the scene is producing different amounts of blur in, let's say, different parts of the scene. But if you showed a fronto-parallel scene, then what you would get is a spatially invariant blur, because all the blur circles will be at the same radius, and therefore you will get just one uniform blur. Right. So let me just show you an example of that here. Okay, so look at this. Okay, this image is an example of this. I just picked up from the web. Okay, picked it up. So are you able to see it? Do I zoom it? Okay. So this is the case of space invariant blur. Okay, you know that you can see that it's not very sharp, but then the sharpness does not, or the degree of blur does not change as you walk through the image. Right, wherever you go, it's the same blur. So this is like a plain wall, no? This is like a wall, and then therefore you can imagine that either it will be totally focused or it will be totally blurred, but the blur is going to be uniform in the sense that it's invariant. It's the same wherever you go. Whereas if you had a scene like this, yeah, right, this is if you had something like that, okay, a wall which is actually inclined. This is also a wall, by the way. This is like a library, and you can see it's like a library rack, and you see that the blur is varying, and this is all optical. Okay, there's no motion here, right? This is all optical kind of a defocusing, and you can see that the blur is changing as the camera focused. As the camera is focused only with respect to objects that are near, and then those objects that are far away will get blurred. So this is an example of how a space variant blur looks like. Okay, and you should be able to map it back to the way that you could actually visualize how this image might have gotten formed, right? So you have a 3D scene, and how different blur circles and all must have come together to give you this kind of an image, right? So that's the image formation part, and we'll again get back to that later. Okay, why this formation? Why this can help us understand many other things also. It's not only to understand image formation in pinhole and image formation in lens. It is also something that we can exploit later for other things. In fact, you know what? When you see this, it tells you something. What does it tell you? Huh?
The right side is closer to the viewer.
Sorry? What is the?
The right side of the image is closer to the viewer.
Closer to the viewer. Yeah, closer to the camera, let's say. And what is it? Someone, I thought I heard something from here. Huh? Exactly, right? Yeah, she is correct. So what it is saying is that the scene that you are actually looking at has a 3D variation, because the blur is changing, no? Otherwise, you would not have found a change in blur. Either it would have been all focused, or it would have been all blurred the same way. You wouldn't have gotten a variation in the degree of blur. It looks like in the front it's less, and then somewhere else it's more, which means that the lens is actually looking at a 3D scene. So it is like acting as a cue for depth. So if you are smart, you should be able to exploit that to maybe tell that this scene is actually 3D, and then even go further and sort of maybe make inferences about which object is where, right? How far away and so on. We will come back to that later. Okay, what is called depth from focus and so on. But as at this point of time, okay, it's enough to just walk through these examples. All right, now what happened? Okay, so a lens is LSI.